Okay, let's unpack this. Welcome back to the deep dive. Our mission today, well, it's a really focused immersion into a piece of flight instrumentation that's just absolutely fundamental for your upcoming ATPL theory exams. We're talking about the turn and slip indicator. And our goal isn't just, a quick summary. We're here to extract those exact knowledge nuggets, the specific physics, the calculations you really need to confidently answer those high-yield, sometimes tricky questions the examiners like to throw at you.
Yeah, and what's fascinating here, I think, is how such a seemingly simple instrument, on the face of it, manages to fulfill two entirely separate but crucially interdependent roles.
Right.
It's a combined display. You've got one part, the rate gyro, measuring angular velocity, how fast you're turning, and then the other part, the ball, basically measuring lateral acceleration or, are you balanced? For effective instrument flight and definitely for nailing those exam questions, understanding that relationship between the turn rate and the balanced application of force, that's paramount. We really need to focus on the physics gyroscopic principles, precession, centrifugal forces, because that's where the core knowledge lies, defining the difference between a nice, clean, balanced turn and an unwanted slip or skid.
That's a perfect starting point. That dual role is probably the first key structural concept we need to sort of lock in. Two distinct measuring devices sharing one instrument face. So first up, we have the rate of turn indicator. That's the needle. This is the, let's say, the complex component. It relies on a carefully calibrated rate gyro to precisely measure the rate of turn about the aircraft's vertical axis.
And second, we have the deceptively simple slip indicator, the classic ball. It looks basic, but it's doing a critical job. It's essentially a pendulous device. Its only function is to tell you, visually, if your turn is truly balanced. Is the angle of bank you've established exactly correct for your current true airspeed, your TAS, and the rate of turn shown by the needle? It's like the immediate feedback loop, the safety check, making sure you're coordinated.
Yeah, and getting those two mixed up on the exam, what the needle measures versus what the ball measures, that's an easy way to lose marks. So let's start with the heavier lifting, I suppose. Section 1. The rate of turn indicator and the detailed physics of the rate gyro. This is where we really break down the engineering behind the needle. Okay, so the mechanical blueprint first. This isn't like an artificial horizon or a directional gyro, is it? Those are built for high rigidity, stability. The turn indicator uses a very specific setup, a horizontal axis rate gyro. What does that configuration immediately tell us about how it works and its limitations?
Well, it tells us two really key things that make it fundamentally different from those other gyros you mentioned. First, its spinning rotor axis is horizontal when the aircraft is in straight and level flight. Second, and this is absolutely crucial for your exam prep, it has only one gimbal.
One gimbal.
Just one. And therefore, it only has 1 degree of freedom. We deliberately restrict its movement. It's not free to tumble around like a standard gyro.
So if the aircraft pitches up or down or rolls side to side without turning, that rotor axis just stays horizontal relative to the aircraft. It doesn't react to pure pitch or roll.
That's the idea. It's designed to ignore those motions. But the moment the aircraft yaws, rotates about its vertical axis, which is the definition of a turn, that single gimbal becomes a constraint. It prevents the rotor from just maintaining its orientation in space like a free gyro would try to.
Right, because the airframe itself is turning.
Exactly. The airframe, and therefore the fixed frame holding the gyro assembly, is rotating during the yaw. This applies a force to the gyro rotor through that single gimbal connection.
And because there's no freedom for it to move out of the way in that direction.
Correct. The frame applies a force, and this generated force is what we call the primary torque. And as we know from gyrophysics, applying a torque to a spinning rotor doesn't cause it to move in the direction of the torque. It causes it to precess.
So we're actually using precession here, harnessing it.
Precisely. We are deliberately using the principle of precession to create a measurable output, a tilt, which is then linked to the needle.
So just to be absolutely crystal clear for the exam.
All right. Many thanks for listening to this free part of the ATPL Theory podcast. If you want to continue learning and access the full comprehensive guide, go to my Patreon at patreon.com/ATPLtheory or my Hero at herohero.co/ATPL. That is patreon.com/ATPLtheory or herohero.co/ATPL. Wishing you all the best